So today we're going to be learning how to use synthetic division, and today we're going to be dividing by a linear factor in the form of x plus c. If it's in the form of ax plus c, we have to convert it. So we're going to see that some we're going to have in the form of x plus c, and some later on we're going to have a constant. So just as a disclaimer, the band is practicing during these times, so you may have some melodious music as you listen to these equations play on your screen. Right now they're warming up, so melodious might not be the right term, but as we go on, you'll get to hear some nice music playing on. So let's go ahead and get started. So synthetic division is a way to speed up polynomial long division. And one of the reasons why we can do that is, let's take a look at what would happen if I try to divide this longhand. I would take the x plus 4, I'd put it on the outside, and I'd have my x cubed plus 8x squared plus 20x plus 16. And I'm going to color this up to see if maybe we don't notice a pattern going on. So the x and the x cubed, we notice that we get an x squared right here. Basically what ends up happening is, because I have a single x and I have whatever this is, my number is going to be exactly the same. So I'm going to highlight this in red. So notice my 1 is my 1. There is no change. As I work this out, I have 1 times 1, so I get my 1x cubed. And then notice my 1 times my 4 is going to give me a 4. So 4x squared. I know that I'm going to have to change my signs, so my positive 1 and my positive 4 is going to change to a negative 1 and a negative 4. And I'm going to combine these, of which these cancel out. My 8 and my negative 4 are going to give me a 4. Then I'm going to drag down my 20, so plus 20x. Okay, and so I notice that again, that number right there is going to travel all the way up to my top. I guess I should have done this in green, so plus 4, because again, with a linear factor, that number and that number are going to end up producing the same number. So I have a 4x. And what this will do is I'm going to multiply the 4x times the x, and I get another 4x squared. And then I multiply 4 times 4, and this time I get a 16. Again, I'm going to need to, when I change these, or when I take the difference, I'm going to have to change the sign, so minus 16. Minus, those are going to cancel out, and I'm left with a 4. And I'm going to drag down my 16. And then I'm going to take this 4 and I'm going to move it right back up to the top, so plus 4, which is going to allow me to say x times 4 is 4x, and then 4 times 4 is going to give me a 16. I'm going to have to change the sign here in just a minute, so that when I combine these, they cancel, and I have a 0 remainder. Now, let's see if we can't notice a pattern here. Now, I highlighted some in red, which means that I want to look for these things. You notice there isn't one right here. I'm not actually combining, so I'm going to box this up right there. So, synthetic division, basically, we're trying a linear factor. So this was a lot of background information. We already know how to do this. I want to test to see if this is a factor of this, which means that if I plug this number, if I plug something that makes this 0, I should get 0 up here. So I'm going to test the root. So I'm going to say x plus 4 is equal to 0. If this is 0, then that should be 0. So I should get technically a 0 over 0. Let's see if I can make that work. So if I subtract my 4, x equals negative 4. So I want to try and plug in a negative 4. So let's go ahead and let's take a negative 4. Now what I'm going to do is I'm going to list my coefficients. My coefficients right here are, let's do purple. I have a 1, I have an 8, a 20, and a 16. So 1, 8, 20, and 16. So what I'm going to do is on the first term, I'm going to drag down my 1. And let's write this in green. So I have my 1. And I'm going to do a series of steps where I am going to multiply. So negative 4 times 1 is going to give me a negative 4. I'm going to combine these two. So I'm going to say 8 minus 4 is 4. Then I'm going to multiply again. Negative 4 times 4 is negative 16. And then I'm going to combine 20 minus 16 is 4. Then I'm going to say, okay, negative 4 times 4 is negative 16. And I'm going to combine these. 16 minus 16 is 0. So what I've noticed is the fact that when I plug in a negative 4, this is actually synthetic substitution, this setup. When I plug in a negative 4 into this equation, what I get is I get 0. Which means that, yes, this is a factor of the thing above it. Let's take a look at what we just saw right here. So 1, it stays the same. When I take my 8 minus my 4, that's going to be what's happening in my second term right here. And I get a 4. When I work at the next step, I'm going to get a 20 minus a 16. The result is going to be a 4. And then as I work the next step, I'm going to get a 16 minus a 16, and I'm going to get a 0 remainder. So we see that this visually is setting up the same algorithm that's going on with long division, but it's a much easier process to work. So let's go ahead and let's try that one more time without all the fluff of working this over here. So what we've got right here is I'm going to take this and I'm going to test the root, which means my n minus 2, I'm going to set that equal to 0. Oh, and before we move on, the other thing that we can do is our answer, when I divide that out, is I'm going to count up. I'm actually going to do this in, let's do this in purple. No x's. I'm going to get a single x and an x squared. So positive and positive. And that is my answer if I were to actually divide that out, which we see is going to be the same thing as right here. Super easy. No x's, 1x, 2x. If I continued on, I'd keep counting up. So knowing that, let's move back into this equation. So I'm testing the root, n minus 2, n equals 2. So I'm going to plug that in. So a positive 2. I'm going to take my coefficients of 1, negative 5, 2, and 8, and I'm going to plug them in. I know for my first term, I'm going to get, I'm just going to do this in, yeah, I guess I can keep doing it in green. 1, I'm going to multiply the two numbers. So 2 times 1 is going to give me a 2, and I'm going to combine. Negative 5 plus 2 is negative 3. I'm going to multiply. 2 times negative 3 is going to give me a negative 6. Combine to a negative 4. Multiply to a negative 8. Combine to a 0, which means, yes, this is actually a factor or a root of this larger polynomial. And so that would mean that if I count my way up, no x's, or I guess in this case, no n's, 1n, and n squared. And so again, let's double check. I'm going to check the long way with polynomial long division and see if we can get the same answer. And so I take my n minus 2, and plug it into n cubed minus 5n squared plus 2n plus 8. Okay? And I'm going to speed this up a little bit so we can check to see if this all works out. Okay, and so what we notice is that yes, in fact, indeed, we get the same thing. Our two answers match. This was just a lot faster. And so logically, the next thing you might ask is, okay, well, if I can set it up like this, what happens if I have a coefficient in front of my variable? So I have a 2n plus 2. I don't have an n plus or minus something. And we mentioned earlier that it has to be in the form of a single variable plus or minus a number. If it has a number, if it has a coefficient in front of the variable, we have to convert it. Well, what does it mean to convert it? Well, let's test the root, which means 2n plus 2 is equal to 0. I'm going to subtract my 2, so 2n is negative 2. I'm going to divide by 2, n equals negative 1. I'm going to test that. So negative 1, take my coefficients of 24, 18, negative 36, and negative 30. I'm going to drag down my first coefficient to get started. So 24. Okay. Multiply, negative 1 times 24 is negative 24. Combine those together, that's going to give me a negative 6. Multiply those, that's going to give me a positive 6. Combine them, that's a negative 30. Multiply them, that's going to give me a positive 30. Combine those, that's going to give me a 0. And so the answer is yes, that is a root, or that is a factor. That took all of maybe 5 seconds. Now let's go ahead and let's double check our work in long division. So again, I'm going to speed this up and check to see what we did. And so yes, we do notice that it has a 0 remainder, but we notice something. My answer in this case is not the same as my answer when I plugged it in over here. And why might that be the case? Well, think about it for a second. When I plugged in my negative 1, I'm testing out this root. Now this root actually has a factor in it. And the factor is what we've pulled out of that front end. If I were to undo this process and reconvert that back to 0, I would have an n plus 1 is equal to 0. Is that the root we actually tested? No. It looks like what we've done is we've factored out 2 n plus 1. And so we tested this part of the root and we pulled out the factor of 2, which means I only divided by an n plus 1. I have to then divide by that factor that I have pulled out, which means I'm going to cut all of these in half. So that 24 becomes a 12, that negative 6 becomes a 3, and that negative 30 becomes a 15. And now they match. Add in my n and add in my n squared. There we go. So something to note in the future is if I pull something out, go ahead and divide my final answer. Let's do one more just to make sure we got that. So what we notice is the fact that I'm going to be pulling out another 2 out of this one. I have a 2x plus 4. When I test my root of 2x plus 4, I know that's going to be a 2x equals negative 4 and an x equals negative 2. That's going to be what I'm testing. If I resolve, that's going to be an x plus 2 is equal to 0, which means that I must have pulled out a 2 out of that. So I'm going to be testing negative 2, but realizing that I've pulled out a 2, I'm going to divide my final answer in half, and I should get my final result. So let's go ahead and set that up. Perfect. There we go. I'm going to drag down my first one. That's going to give me a 6, I'm going to multiply, give me a negative 12. Combine gives me a negative 18. Multiply, 36. Combine, negative 108. Multiply, 216. And combine, 0. I know that because I pulled out a factor of 2, I'm going to cut all of these in half. 3, negative 9, and negative 54. I'm going to add, in this case, my x and my x squared, and I'm going to see if that is what I get by using long division. So again, let's speed this up so we can check to see how we're doing. So yes, in fact, our answer does work when we divide it by 2. So we know that that trick works right here. So the last question, what I want you to do is I want you to pause the video. I want you to try out number 9. Unpause it when you're done and see how you did. Okay, so let's take a look. I know I'm going to be testing the root, which means my 2x minus 3 is equal to 0. I'm going to add the 3 and divide by 2. I'm going to be testing that out. So 3 halves is what I'm plugging in. If I reset that, x minus 3 halves is equal to 0. It looks like I must have factored out a 2. So now I'm going to have to divide my answer again by 2. So 4, negative 5, and 3. 4. So 4 times 3 halves, that's going to be 2 times 3, which is going to be a 6. It's going to be a 2. 3 halves times 2 is going to be a 3, which in this case is going to be negative 2. Multiply again, that's a negative 3, combined to get a 0. I know then I'm going to take that 2 and I'm going to divide everything in half. So 2, 1, negative 1. I have an x and an x squared. I'm going to make that a plus. Boom. And there we go. So again, I'm going to double check this last one last time to make sure we're good. And yes, our answer for polynomial long division checks out. And there we go. So today we're going to be using synthetic division on a denominator that is not a linear factor. And there's going to be a trick to solving these, and the idea is that we can still use synthetic division because it's such a powerful tool if we factor the bottom. Because then if I factor this bottom, I can plug in each linear factor and work it twice. The same idea is, let's take a constant. If I took, let's say, a number 24, and I divide it by something like this, which is a combination of two factors, let's say 12. And I'm like, 24 divided by 12, that's too big of a number. I can't figure it out. How would I break 12 into two different things? How would I break 12 into a 2 and a 6? Well, what I can do is I can take 24 and divide it by 2 and get a 12, and I can divide the 12 by 6, which will give me a 2. I can break it down into a two-step process. And that's exactly the same as what we're going to be doing right here. We're going to break down this quadratic factor on the bottom. And I'm going to turn that, because this is a difference of squares, I know that is going to be an x plus 3 and an x minus 3. And I'm going to use synthetic division to divide that into the first, and then take my answer and divide the second one in. So let's see how that works. My first one right here is I'm going to label it as my first factor. If I solve that equal to 0, that's going to be a negative 3. So what I'm going to do is I'm going to take my, I'm going to do this in black, my coefficients, which is a 1. Again, I notice I'm missing a term of 0, negative 45. I'm missing another term of 0, and then 324. And so let's see how this works out. Carry my 1. I multiply and combine. Multiply and combine. Multiply. Let's see, that's going to be 3 times 30 is that's positive 90. 3 times 6 is 18, so that's 108. And combine. Multiply and combine. Perfect. So I've successfully divided this out of the polynomial, and I'm left with this. Now the cool part is, when I go for my second term, I don't need to change anything. I can just say, okay, set that equal to 0, which would be a positive 3, and I'm ready to go. So let's set this up. 1, combine, multiply, combine, multiply, combine. Perfect. And so now I know that this is my answer of, let's count our way up, that's a single x, and that's an x squared. So I have an x squared minus 36 is my answer. Perfect. And so we see we just break it down into a two-part process. So why don't you try the next one, give the video a pause, give a shot at number 3, resume it when you're done. Okay, so what you should have done is you've noticed the fact that, again, this is a perfect square, or a difference of squares. So I'm going to convert that into an n plus 5 and an n minus 5. We know if we FOIL that out, we'll get an n squared minus 25. So I'm going to do my first factor first. If I set that equal to 0, that's going to be, I'm going to have to subtract the 5, so negative 5. Set up my coefficients, 1, skip a term, negative 29, skip a term, 100. And let's see how we do. Drag down my first term, multiply, combine, multiply, combine, multiply, combine, multiply, combine. Super fast, super easy. Now I'm going to go for my second term. If I set that equal to 0, I have to add the 5, so it's, draw it a little higher, positive 5. That way it lines up properly. Okay, so drag down my first term, multiply, combine, multiply, combine, multiply, combine. Perfect. So we've got our answer here. If I count my way up, that's an n squared. So now my answer is going to be n squared minus 4. Boom. Hopefully you did pretty well. The only time that we might have a little bit of issue is from one of these that we've seen that has a coefficient out in front of it. Now, we recognize that this is also a difference of perfect squares. So I'm going to take the square root and the square root. So I'm going to have a 2x plus 10 and a 2x minus 10. And now what some of you may realize is the fact that I have a 4, 100, 16, 436, and 900. All these are divisible by 4. And you can, in fact, factor out a 4 and divide everything. And that'll make your life a lot easier. Now, one of the things that I'm going to show you is how to work with synthetic division, ignoring that, and just how to work your answer towards the end. So, if I were to set this equal to 0, that would become a negative 10 divided by 2. Negative 10 divided by 2 is negative 5. So I'm going to take that, and then I'm going to divide my answer by 2 at the end. So 16, skip a term. Negative 436, skip a term, 900. So what we're going to do here, 16, multiply this, so that's going to give me a 50 and a 30, 80, combine it. See, that's going to give me a positive 40, so 400, negative 36. Combine that, that's going to give me 150 and 30. It's a positive 180, 80. Let's see, that's going to give me a negative 900. 0. Perfect. And now, right here, a lot of people would want to jump into the second equation, but let's not forget that when I solved this, my 2x plus 10 is equal to 0. If I subtract the 10 and divide by 2, and then resolve for x plus 5, this is not the factor that I'm working with. So you can still work with your top number without having eliminated any variables. And all you need to do is factor out that at the end. So I'm going to divide everything by 2. So it's going to be an 8, negative 40, that's negative 18, and 90. That is when I jump in with my next one. So I'm going to take a positive 10 over 2 or a positive 5. And I'm going to do it again. So you carry the 8 down. 5 times 8 is going to give us a 40. Combine, multiply, combine, multiply, combine. Then I'm going to divide it by the 2. So I'm going to get a 4, 0, negative 9, which if I carry my x's up, x squared, that means that my answer is a 4x squared minus 9. Boom. And there we go. So now let's try it with something a little different. Let's try, instead of something with a difference of squares, let's try something with this thing. Now, normally I would have to factor this, but oftentimes you'll notice that, hey, this is a perfect square trinomial. So we can factor this into an x plus 5 squared, which means I'm going to try the same root twice. So I'm going to plug in the negative 5 and work my way down. So my coefficients are 1, 18, 121, 360, 400. Draw my line. Carry my 1, multiply, combine, multiply. Let's see, that's going to be combine. See, that's going to be 61 minus 5. That is going to be 56. That's going to be 250 and 30. That's 280. It's going to be a positive 80 and a negative 400. Boom. So that was my first iteration. The second iteration is going to be the same thing. I'm going to do a negative 5. There's not two factors because the two factors are the same factor. Work this out. Carry my 1. Let's see, multiply, combine, multiply, combine, multiply, combine. Boom. Carry my x's up. So that means my answer is x squared plus 8x plus 16. Boom. And so for the last one, what I want you to do is I want you to pause the video, try the last one, unpause it when you're done, and see how you did. If you can knock this one out, you can pretty much knock out any synthetic division for any problem. Okay, perfect. Let's see how we're doing. We should notice that this is going to be a perfect square trinomial, which means that if I look at this, I'm going to factor this down into a 4n plus 1, or 2n plus 1 squared. So 2n plus 1 squared, which means I'm going to have 2 iterations of this. So my first iteration, let's see, I'm going to subtract the 1 and divide by 2, is a -1/2. I know I'm going to take my answer and divide it by 2 when I'm done. So 16, 64, 88, 48, and 9. 16, half of 16 is 8. 56. Half of that is going to be 25 and 25 and 4 is, or 25 and 3 is going to be 28. So -28, which is going to bring it down to 80, 60. Half of that is -30, 18, -9, 0. Boom, cut all these in half. 8. See, that's 25 and 3 is 28, 30, and 9. And this is where we do the second iteration. So -1/2. My lines are getting a little cattywampus here, but oh well. 8, -4, 24. Half of that is -12. 30 minus 12 is going to be 20, 18. Half of that is -9. Hold my 0. Cut those all in half. 4, 12, 9. Perfect. Count my way up. So that means this is going to be 4n squared plus 12n plus 9. There we go. So today what we're going to do is we're going to be graphing polynomials. Polynomials, now we're not going to graph a true polynomial, meaning each point along the curve. We're going to be graphing what I like to call a skeleton graph, which is it's going to highlight the zeros along the graph, and then a couple interesting points like local maxima, local minima, and it's definitely going to tell us the end behavior. And the way we're going to do this is by performing a sign test. And the most important thing as we go through this is if 2 roots, or more roots really, but basically if 2 roots exist on the same point, that point is the local maxima or minima. Now if we have things like 3 roots existing at the same point, something special will happen. But today all we're going to focus on is if 2, that point is the maxima or minima. But, well, what does that all mean? Well, let's take a look. So with this polynomial, it looks like I have 1, 2, 3 roots, and I'm going to graph them at, let's see, if this one is x minus 4 is equal to 0, x minus 6 is equal to 0, and x plus 2 is equal to 0. That's going to give me a root at 4, at 6, and at -2. So I'm going to go ahead and I'm going to put those points on my graph. I'm going to start out, I'm going to put my y-axis a little farther to the left, seeing as I have some bigger positives. Let's go ahead and do that. So if I have a root at -2, at 1, 2, 3, 4, and at 6. Now that's going to tell me I have one of 2 different shapes. I can either have a shape going up, down, and up, which would cross my axis 3 times, or option 2 would be down, up, down, which still cross my axis 1, 2, 3 times. So in order to figure out which one it is, I'm going to perform a sign test between my points. And so let's see how that would look. Well, I'm going to pick a point between -2 and 4. So just for easy number's sake, I'm going to pick 0. So if I plug in a 0, I'm going to get a negative. So here's what I'm going to do. I'm going to say for this point, I have a 0 minus 4 is a negative, 0 minus 6 is a negative, and 0 plus 2 is a positive. So a negative times a negative is a positive, times a positive is a positive. So I know at this point, my graph is curving up. because my end result, I don't actually know how far up it goes, but I know it goes up. Could be up a little higher, it could be up really high, or it could be up barely anything at all. Again, we're not actually graphing the polynomial, we're graphing a rough sketch to see what the general shape of it looks like. So I know that my end result is going to be positive. Now, secondly, I'm going to check a point between here. So between 4 and 6, I'm going to plug in the number 5. So 5 minus 4 is going to be 1, which is a positive value. So positive. 5 minus 6 is going to be negative 1, so that's a negative. And 5 plus 2 is going to be 7, so that's a positive. Again, I don't actually care what the value is. I'm just looking for the sign. Is it above or below the axis? So positive times positive is positive, times negative is negative. So I know between these two roots, my graph is negative. It's below my x-axis. And then now, here I have a local maxima, right there. I have a local minima, right here. And now I'm looking at my end behaviors, what the graph is doing outside of the roots as x approaches infinity and x approaches negative infinity. Well, I do the same thing. I perform a sign test. So let's plug a number a little higher up. Let's say 7, or 10, or 100. Let's see, 100 minus 4 is going to be 96. That's a positive. 100 minus 6 is 94. That's a positive. 100 plus 2 is 102. That's a positive. I know 3 positives multiplied together is going to give me more positives, so I know the graph continues to go towards a positive direction. And likewise, seeing as it's probably going to go straight through, I bet you this is going to be a negative. So let's pick a number like negative 100. So negative 100 minus 4 is negative 104. Negative 100 minus 6 is negative 106. Negative 100 plus 2 is negative 98. So 2 negatives would be a positive, but a third negative is going to mean that that is negative once more. So I have the rough sketch of my graph looks just like that. I have a local maxima between these roots, a local minima between these roots, and my end behavior is as x goes towards infinity, so does y, and as x goes towards negative infinity, so does y. Perfect. And that's this rough sketch of a polynomial. Let's try one more to make sure we understand the concept of what we're doing. So again, I have 1, 2, 3 roots, which means that I'm going to have 0 and x plus 3 is equal to 0. So 3, negative 3, and that one's already solved. So, well, this one's nice and centered, so I'm going to draw my axis right here in the center. Cool. So I have 3 roots, 1 at 0, 1 at positive 3, and 1 at negative 3. And so I just want to perform a sign test between these roots and on the outsides to see which way it's going. So let's go ahead and let's test between 0 and negative 3. So I'm going to test the point negative 1. So negative 1 times, that is negative 1, so it's a negative. Negative 1 minus 3 is negative 4. Negative 1 plus 3 is 2. No, I don't want to put a 2, I just want to put the sign. So negative times a negative is a positive, times a positive is a positive. So my graph is up right here because the overall sign is positive. Do the same thing between these points. So let me try the positive one. So positive 1 means positive. 1 minus 3 is negative 2. 1 plus 3 is positive 4. So positive times a negative is a negative. Negative times a positive is still a negative. So my graph is negative between these two roots. It goes below the axis. Likewise, I can do the same things on the ends. Let's see, 100, if I plug in a number way over here, positive. 100 minus 3 is 97, positive. 100 plus 3 is 103, positive. So the graph continues up. As x approaches infinity, y approaches infinity. Likewise over here, if I plug in negative 100, negative, that's going to be a negative 103, and a negative 97. Two negatives make a positive, times a negative is a negative. Boom. And there we go. So what I want you to try and do is I want you to try the next one and see if you can't figure out what's going on. If you notice that I have two right here that are exactly the same. So x minus 2 is 0 and x minus 2 is equal to 0, which means I have a root that exists twice. So again, go ahead and pause the video and see if you can't figure out what's happening with those two roots. Okay, so let's see. I'm going to go ahead and move my axis over here, which is going to allow me room for that negative 9. So I have my y. And I have a root at 2, root at 1, 2, 3, 4, 5, 6, 7, 8, and 9. And then I usually like to know that because I listed it twice, I'm going to draw a second circle around that. Now, this isn't anything mathematically accurate per se. That just lets me know, hey, there's two roots here. One for the dot, second for the round dot. So let's go ahead and let's try out a few things. I'm going to test the number between my two listed roots. So how would I plug in a 0? Just because zeros are nice and easy to figure out. So 0 minus 2 is negative 2. 0 minus 2 is negative 2. 0 plus 9 is a positive 9. So that means my graph goes up throughout here. So I'm going to go ahead and I'm going to start going up. But I'm going to pause right here because you'll see what's about to happen. So as I test to the left, if I plug in a number like, let's say, negative 100, well, that's negative 102, negative 102, negative 91. So two negatives make it positive, times that gives me a negative. So I know what the leftward behavior is, but I haven't quite finished this arc because when I see a 0 pop up more than once, something funny happens here. So let's plug in a number to the right, and we would expect for it to go through the 0 and keep going negative, right? Well, let's try it out. So if I plug in a number like 100, 100 minus 2 is 98, positive. 100 minus 2 is 98, positive. 100 plus 9 is 109, positive. So whatever's going on, my graph is going to be going up. So at no point does my graph dip below the axis. So how would that look? Well, if we remember from earlier on, if two roots exist at the same point, then that point is the local maxima or minima. So it is the top of the hill or the bottom of the valley. Or I guess you'd say the top of the crest or the bottom of the trough, which would mean that it's going to curve like this, curve through there, and it's going to continue to curve without actually going below the axis all the way up. So it's going down, touches it, going up while still touching it, and keeps going. So if you see a point like that, just know that it's not going through the 0, it's bouncing at the 0. So now that you've seen that, let's try another one that bounces at a 0. Let's try this. So go ahead, pause the video, see if you can't figure this one out. Okay. So this one I have x equals 0. And if I were to write this out long way, I would write x minus 9 is equal to 0, x minus 9 is equal to 0, which would give me 2 at 9. So I'm going to go ahead and put my root, or put my axis over here. Y. There we go. I'm going to put a 0 at 0, and then 1, 2, 3, 4, 5, 6, 7, 8, 9. I have 1, 0, and 2, 0. So I know at this point, it's either going to curve up through or it's going to curve down through. It's going to bounce at that point. And so really, all I need to do at this point is say, okay, let me test the point between here. Okay, let's try 5. So 5 is a positive. 5 minus 9 is negative 4. And that's going to be a negative twice. So negative negative is a positive times a positive. This graph is going to be in the positive value right here. And so technically I know if it bounces right here, what it's going to do is it's going to curve down. It's not going to go through, but it's going to bounce. And under here, because that's not a double root, it's going to curve straight through. So I only actually need to test one interval. And if I know how many times that root is listed, I know what behavior is going to happen at that root. And now we could go ahead and we can test and prove this, but what we're seeing is the fact that if it's positive right here, that root is listed once, which means it has to change signs over here, but it's going to bounce right there. So, much faster method of solving it. Go ahead and try this one. This one, instead of having 3 roots, it's going to have 1, 2, 3, and 4 roots. So go ahead, pause the video, see if you can't figure that one out. Okay, so let's see how you did. So I have a root at 0. 2x minus 5 is equal to 0. I'm going to list this one twice. So 2x equals 5, x equals 5 halves, x equals 5 halves. I'm just going to go ahead and write it twice because, cool, I have 2 of those. And then 4x minus 5, 4x equals 5, x equals 5 fourths. Cool. So I have 0, 5 halves, and 5 fourths. Let's see, those are both positive, so I'm going to put my axis over here on the left. Give me some room over there on the right. Actually, because these are so small, they're fractions, I'm going to make these by, let's go with the smaller of the 2 fourths. Which means 0 is 0. And if that's 5 fourths, 1, 2, 3, 4, 5 fourths. Let's see, if that was a fourth, that means I'd have to double it. So that's going to be 10 over 4 and 10 over 4. So 5, 6, 7, 8, 9, 10. Perfect. And so really all I need to do is test the sign between 2 of these points. Technically I could test between 2 of these points, or I could test the end behavior. So let's try the end behavior this time. Negative 100. Negative 100 times negative 4 is positive. Negative 100 times 2 is negative 200. Minus 5, that's definitely a negative. Because it's squared, I have another negative. Negative 100 times 4 is negative 400. Minus 5 is negative. So negative makes a positive. Times a positive is a positive. Times a negative is a negative. So I know it's going down over here. Basically, I'm going to track my zeros. That's a single root, so it's going to go completely through, which means it's going up, and it's going to curve up all the way until it hits this point. It's a single root, so it's going to go straight through, and it's going to curve up. And because this is a double root, it's not going to go through, it's going to bend. It's going to bend right here and bounce at that point and curve back down. And there we go. We have ourselves graphing polynomials.